Yes,
Yeah.
sir, you can start now.
Yes, sir.
Please
Yeah.
start.
Okay, first of all, I would like to thank Professor Rudra Pratap, Professor Anand Suresh for inviting me to give this memorial talk, and thanks to Dr. Sunil for nice introduction. So the title of today's talk is Electronic Skin with Distributed Sensors and Computing. And uh, so before I start, I would like to give a brief introduction about our research in my group, which is Bendable Electronics and Sensing Technologies Group. So what we do in Glasgow, we try to understand sense of touch in humans, use this knowledge to create skin, electronic skin for robots and for artificial for any other objects, and then the technology that is developed for robotics can also be used to improve quality of life for humans, either through wearable devices or touch-enabled prosthetics, etc. So in that sense, we close the loop, we bring the technology back to humans. Uh, Here are some examples of electronic skin, various variants of skin and 3D printed hands that we have developed. For example, in the center is iCup with large area electronic skin. There's a POSFET tactile sensing array here on the integrated on the palm of iCup, the same robot. Then there's a 3D printed hand, which has embedded tactile sensors inside the structure itself. There's a graphene-based skin that you see here on the eye limb, and then another example of 3D printed hand shown here. We also work at the interface of virtual world and the real world, and in that context, we have developed our own demonstrators. What you see here is a hologram, which is interactive hologram. There are 3D mid-air display of 3D objects, and you can control these objects either through gestures, as you can see here, or you can also feel these virtual objects as you see here, an interactive 3D model where you can see globe, mid-air globe, and you can lift it, as well as there will be another example of a artificial or a virtual push button that will just come, you will see, and when you try to push this button, you can also get a sense of pressure. So that's the push button. When you press it, you get the haptic feedback, and not just sense of pressure, you can also get sense of temperature. So touch sensing is pretty much important in scenarios, whether it is interaction with real world or with virtual world. And that underlines the importance of electronic skin, which is the focus of this talk today. But before I start my talk, I would like to acknowledge the support from my group members. What I'm going to present is essentially their hard work. So here is the outline of my talk. The first section, I will describe motivation for developing electronic skin. Why do we need electronic skin in various scenarios, as well as some future scenarios where electronic skin may enable advances. And then I'll move on to the electronic skin technologies, essentially covering all aspects related to integrated sensing and integrated computing. And this section is divided into various time scales in terms of technology available immediately, technology that could be used, that could be developed in midterm, and then in the long term, as well as the solutions from nanoscale to large area. And when I say large area, I normally refer to areas bigger than the largest wafer that is available to realize electronics. Finally, I'll conclude this talk and I'll present with some references and acknowledgement to my funders. So let's go to the first section of this talk, why electronic skin. This video highlights the importance of the touch sensing even before we see the world. In the womb itself, the only sensory modalities that is available is sense of touch. And through sense of touch, there's a huge interaction that is taking place between the with the mother. That itself highlights the importance of sense of touch. But taking example of a real world, If you try to put your hand on the ice block for some time and then grasp an object nearby, then you will see that object, it will be difficult for you to grasp object will slip out of your hand. And you can see this is slipping out, but you can do nothing about it because temporarily your touch sensing you lost the touch sensing, and that's again highlights why touch sensing is important. And if this touch sensing is important, then this real question comes, why are we developing prosthetic limbs which do not have any sense of touch, or other machines which do not have sense of touch? An example include robotics and automation. If you see this example, robots are working in cages and you do not see any humans in this cage. And by chance, if by any by chance, if a human enters into this space, we come across news such as this one: robot kills Manson Volkswagen plant, or an example even from Gurgaon in India, and another example from Japan. So why are we then creating, question comes, why are we creating machines which even by accident they end up harming humans, a skilled worker? If there was in previous video, if there was a robot with some skin like structures so that they can sense the human approaching their workspace and they could stop, then such incidences could be avoided. And this will become even more important in future, because we talk about Industry 4, where robots and humans are expected to work together as co-workers. And when you expect machine and human to work as a co-worker, the physical interaction, which is mainly through touch, becomes so important that you have to have some means of communication, some means of safe interaction between man and machine. And not only this, there are several push and pull factors that will enable that are important, that enable this research in touch electronics skin. Example is shown here on the slide. If you look at the left hand side, these are the push factors we see today, whether that's application in medical robotics or medical surgery or a laparoscopy, where currently there is no haptic feedback or tactile sensing or tactile imaging which you can gain from. And if you can develop surgical instruments with touch enabled feedback, that will be very helpful. And then on the right hand side are the pull factors, futuristic areas, be the retail, haptic enabled online shopping, or interacting via haptics with the doctor, or neural control of limbs. As you can see on the bottom right, an example where a disabled or elderly person having desire to play with their grandchild, but the robotic vehicle that you see here could be controlled by through brain. So that is the kind of thing. In all these cases, physical interaction is very important. At the center of all these are fundamental questions, which you see here: variety of features of real world objects. For example, what makes different surfaces feel differently when we touch the objects, and why skin and brain work to give, how skin and brain work together to give us a rich experience. We feel so many objects. Unlike vision or audio, touch is so rich in a sense that it allows us to feel how warm objects, cold objects, smooth surfaces or rough surfaces, etc. There are so many things that we need to understand. Okay, so with that background, then question comes is, how can we develop an effective tactile skin? What parameters we need to consider while developing effective tactile skin? And when I say effective, I don't mean to say the skin that is suitable for lab benchtop skin only. It should be useful in real life. And to do that, you have to look at the functionalities, the task, what task the robot will be involved or engaged in. Then you have to look at the hardware. How can I have mechanical aspects such as conformability, flexibility, stretchability? If you look at robotics, there are at the joints particularly, you need stretchable sensors or stretchable electronics. Then there is the aspects related to fast response, and that is very much important, because if you are getting a stimuli, you are sensing something, and there's an action need to be taken based on that sensor feedback, then it has to be fast response. And other aspects such as wiring complexity, etc., need to be considered. And once you consider all these, you have to also then, you cannot forget manufacturing aspects. So this must be manufacturable, easy maintenance, low cost, reliable, and some of these aspects need to be considered. So if you look at the human skin, there are many type of sensors embedded in this soft material, and that's another dimension added to the challenges. You have to integrate sensors and electronics. You have to embed them in soft materials. Current technology, electronics technology, is not sufficient. It has been developed for planar wafer based electronics, and if we have to develop electronic skin with human-like skin, then one has to consider new ways of developing electronics as well. And if you look at again the example, the skin that is shown here, it also comes with variety of sensors. It is not just one sensor that is suitable. You have within pressure sensor, you have two different type of slow adapting and fast adapting receptors present in the human skin. Slow adapting respond to static and quasi-static stimuli, whereas fast adapting respond to dynamic stimuli. Uh, can you hear me?
Yes, sir, you can continue.
All right. Okay. So slow adapting, in a sense, is when you take a typical task of pick and place. So when you are when you are grasping something, at that time it's the dynamic thing. So your sensor have to respond to dynamic events, and normally piezoelectric type sensors are suitable for that. But if you are holding something for a long time, that's where static force sensing comes into picture, and capacitive type sensors are suitable for those events. Then on top of that, there are temperature related receptors, then pain related receptors, and this all comes as a package when you look at the skin over the entire body. So then the next question comes is the can we use the current technology, particularly electronics? Yes, if we can do it, but then we have to redesign robots in such a way that they will have to have planar surface. So then question comes, can we redesign world? Answer is no. And also with the machine we are trying to we have machines which have curvy substrates. And if we look at the humanoid itself, uh, the interaction between human and robot is much better if the robot looks like animal or a human. So that's why there's a lot of focus on developing robots that look like various living beings. There are many type of robots available that have been developed by various groups all over the world. In this case, the eye cup that you see here sitting on the wall, you can see that it's a humanoid robot that has all curvy parts, and to cover that the whole body with electronic skin, you have to have electronics which is not planar. And there are ways I'll discuss in part two. How could we get over with current technologies related to planar electronics? Then we have to think about the large area. Skin is not unlike vision or video. Skin is not centralized, that you have two eyes or two ears. Skin is distributed all over body. All the sensors are distributed. Electronics is distributed. And so you can see all these examples that I was highlighting, embedding in soft material, different type of sensors, distributed electronics, on planar or on flexible substrates. So all this comes as a package when you talk about electronic skin, and it is a complex problem, but it's also interesting because it enables advances in several areas, be it robotics, be it sensing, be it electronics. So there are several areas that are connected. And then we have to look at data, computation, energy aspect. This is another dimension of electronic skin. This is mainly related to how do we handle large data. If we have to look at, I mentioned eyes and ears, these are centralized, you have 2 ears and 2 eyes. So the data amount of data you are collecting is still limited. But if you look at skin, and particularly, if you, as an example, if you see here, the palm area itself has a 5325 mechanoreceptors. These are just rough estimates. In actual, there may be more than much more than this number of receptors present in the skin. And if you add temperature-related receptors and pain-related receptors, this number will be quite high. This means if you have to read all these sensors at the same time, then for each sensor you would need 2 wires, and that means there will be about 10,000 wires just to read the hand. Now, if a robot has to have 10,000 wires, now you can imagine what happens to dexterity. There won't be dexterity. The robot hand will not be, it won't be possible to move the hand. So you have to think about other ways of reading the data. You have to think about this data that you're collecting. There is a limited communication bandwidth. It's same way in humans also. You have to pass on this data to the brain, to the central processing unit, and the bandwidth is limited. So there is simply no way you can transfer all the data and allow brain to process this and then take action, move actuators and take action. It has to be distributed computing. And this is also what human body does. Distributed computing takes place right from the point of the touch, point of contact. At every stage, there's a data, the touch data is processed partially, and by the time it reaches brain, it is just the high level information that brain processes. And this is based on the studies, various neuroscience studies, which indicate that type of thing happening in the skin. Now then the question comes is it requires skin to have distributed electronics. As simple as that. So with these background, I will move to the next section, which is how do we, considering all these challenges, what technological solutions are available, and what can we do in future to address some of the challenges. In particular, I will focus on the distributed sensors and distributed computing, but there are other challenges also related to energy. One example is energy, and I have not covered this part in today's lecture. Going to the first part, materials and what materials and methods are available, which can be used to develop electronic skin with the kind of features I mentioned. And we explored various methods and materials, and we noted that it's not difficult. There are several solutions available. It's just that we have to tweak them a little bit. And first solution that we explored was what can be done immediately using non-bendable technology. So whatever off-the-shelf components are available today, can we put them together to develop electronic skin? So that was in the time scale a quickest thing that we wanted to explore. And in that regard, we got a project called RoboSkin, which was funded by European Commission. And the goal for this project was to develop electronic skin for iCub, which was developed in the lab where I completed my PhD, which incidentally is also acronym is IIT, but this Italian Institute of Technology. So that was the robot developed. This was part of another European project called RoboCub. But this does not have any skin. And if you look at range of tasks, for example, grabbing a heavy sandbag, you don't rely on the fingertips. You just get the feedback from entire body, and you plan the task based on the feedback available from body, and you execute it. So before this RoboSkin was developed, this big part was missing in robotics research. Whole attention was on hand-based manipulation, pick and place kind of task. If you look at other example could be, the animals with not having any limbs, for example, snake. I mean, they rely on feedback from large body parts, and they execute the task nicely. So with that background, we worked on this and we developed the skin. You can see here in this figure. Most of the parts are covered with triangular patches that you see. I'll explain why triangular patches are important. And this is the nicely packaged skin, which is now commercially available as well. So the key point related to triangular patches is the Fuller map concept or triangulation concept, which those familiar with 3D imaging, they would understand the triangulation concept. With small and big combination of small and big triangles, you can develop any 3D surface. And that knowledge we brought in the hardware. So essentially, if you look at a spherical surface, you take triangular projection. From those triangular projections, you can make 2D layout. And once you got the 2D layout, you know that how optimally you can cover this surface with the skin. And if the skin is also made of triangles, the maximum coverage is possible. And that's why we develop the triangulation. We develop the skin with triangular patches. And you can see here, these are the triangular patches. They are on printed circuit boards. No new technology. Printed circuit boards have been known for a long time. One simple example is ribbon of your printers. The same brown color thing that you see in the printers. In that substrate, we realized on top of the substrate was electrodes. You see here on the back side of the substrate, as you see, there are these are the interconnects are routed through the flexible printed circuit boards. On the back side, we have the chip, which is from Analog Devices 7147. It's a capacitance to digital converter chip. So it converts 12 capacitive points into digital value. And that way, on the top of this, we covered this with a soft layer, and soft layer was essentially a capacitive sensor. So the top surface was a conductive fabric here. It was grounded, and when you press the surface, the capacitance would change, and this capacitance change in capacitance is then detected as the amount of force and to detect the contact point. And using this information, then the skin was the triangulation technique also is advantageous because it makes the solution a generic solution. Any 3D surface could be covered with that skin, and we tested it. We evaluated on various type of robots as part of RobotSkin project. So that's iCub, that's Casper robot, which is a robot used to teach or train autistic children. This is a commercial robot. That time it was Aldebaran, now it is SoftBank. And it's a shrunk robotic arm. A industrial robot also was covered with the skin. And that was an example towards safe human-robot interaction in an industrial setting. And what it did to the field of robotics is, you can see here the touch-based interaction, multimodal interaction, touch and vision together, or touch or audio together. That was the new area this skin enabled within the field of robotics. And I have already mentioned about the importance of whole body interaction, which was just missing previously. If you look at the touch feed, the contact from the backside, you're sitting on the chair and you want to leave the chair. It's the whole body, the feedback that you rely on to execute that task. So the skin enabled that new area within the field of robotics. Then it was also by colleagues, the technology was scaled down, and the flexible printed circuit boards were also placed on the fingertip, and you can see the interaction with soft objects. Not only this off-the-shelf components also have been used by. These are mainly master student project results that you see here. They have tried to implement off-the-shelf components in various ways, integrating like embroidery, integrating them on the clothes, and using them for pattern, walking pattern, matching with the pattern, etc., walking pattern and dancing pattern, etc. So they tried this, but not only this. This technology can also be used. Printed circuit boards of based flexible electronics technology could also be used to solve some of the current challenges in areas other than robotics. As you can see here, we developed recently temperature sensor and strain sensor based patch on smart bandage with NFC communication, and this was then integrated on. We tested it on a dummy, on a mannequin, and we noted that it could be quite useful if connected to wearables. It could lead to interesting solution whereby you can monitor the expansion of chest and monitor body temperature in real time. We have developed our app also, and you can see real-time values here. This was a DIY ventilator we developed in our lab itself. So the expansion is picked up here. In this case, these are the real-time signals coming from temperature and the strain of the sensor. So integrating them on clothes, you can think of a wearable system to monitor the potential development of signs of COVID. Okay, then this was all about some solutions that we have in terms of what is available today and how can we repurpose the existing technology to to advanced robotics. But then that is not enough. There are the limited bendability available from off printed circuit boards is one bottleneck. You cannot cover surfaces like pen, where the curvature is small, and you have to then think about new technologies. Furthermore, you cannot have the electronics chip that I was showing is a bottleneck. It's a flat chip. It obstructs the bendability, and then you have to also have think about how can we make flexible chips. In this regard, the solution that we are exploring is based on flexible thin chips, ultra thin chips. And as you see here, it is the new process that we developed is wafer scale production of ultra thin chips. And there are methods available commercially, for example, mechanical grinding, etc. But they lead to thin chips of about 70 to 80 micrometer and beyond that, because mechanical grinding leads to stresses and leads to cracks in the chip. These methods are not very reliable. So we have used a mix of grinding and chemical etching. So what we do is we grind gross etching we achieve by mechanical grinding. Let's say bring the wafer to about 100 micrometer, and then using wet etching or chemical etching, we bring the wafers down to uh, uh, down to uh, down to about 15 micrometer. And the examples are shown here. This is the dummy silicon wafer with different size of the chips. And this is encapsulated. These chips are encapsulated. Bottom is polyimide and top is also polyimide. And thickness of top and bottom or substrate and encapsulation is decided in such a way that the top surface of the chip lies more or less in the neutral plane. Now that's important to have it in neutral plane, because when you bend the chips, they experience stresses, and because of those stress and strain they experience, and because every material experiences this piezoelectric effect is there. So as a result, the device response may change, and neutral plane concept could nullify that. Although I must say that it is quite challenging to have the electronics to have electronics in the neutral plane. There are always fabrication related challenges in this process. So in doing so, we obtained silicon chips that you can see. It is ultra flexible. This is 2 centimeter long and 1.5 centimeter wide. This is bare silicon chip. This is silicon chip on PDMS. We noted that the substrate plays a huge role in terms of bendability. If the substrate is softer, then silicon can be more bendable than when it is present on stiffer substrates such as PET. So we are advancing this now with the phosphate type chips with more electronics on the chip, and then evaluating the overall the concept of ultra thin chips. So idea here is to get complex electronics such as microprocessors, and then thinning the microprocessor and using it along with the flexible printed circuit board concept that I explained earlier. But that's again, this is a kind of solution that we have in sight for medium-term solution. We don't expect it to be a long-term solution. Particularly, there are challenges related to economy, because the chip, if you have to look at the large area skin, then the chip using flexible chips will not be a practical solution. It will be quite costly. It won't be a cost-effective solution. And to that extent, we are looking for, in long term, we are looking to replace this solution with something that leads to also significant advances in electronics, and that relates to printing of electronics. And there are various groups exploring printed electronics, but mostly the research so far has focused on organic polymers, organic semiconductors. What we do is we print inorganic semiconductors, and the reason is simple: mobility is quite high, and that leads to high performance. And high performance is pretty much needed in a range of applications, be it smart cities, be it IoT, wearable systems, etc., where communication and computation need what you need must be at least in communication. For example, about 500 megahertz switching frequency is what you need. So with organic semiconductor, it is quite challenging to achieve that kind of performance for two reasons. Number one is the low mobility. Number two, the technology that we have does not give you transistors with shorter channel length. And both are important. They both contribute to the faster transistor switching frequency. In this regard, what we have done is we are exploring two approaches: transfer printing approach and contact printing approach. So transfer printing approach is pretty much that came from Professor Rogers' group. So what it does is you can realize all silicon micro nanostructures on the wafer, all high temperature processing steps. They are carried out when these structures are still on the wafer. And then you can lift them with PDMS using van der Waals forces. There is good adhesion, good enough adhesion to lift these wires from the wafer. And once they are transferred, you make one more transfer to the final receiver substrate. As an example, in this case, it's polyimide. So once you receive, you have these structures on the receiver substrate. And because these are micro nanostructures, because of their size, it becomes very flexible. And with that technique, solutions such as eSkin tattoo, etc., they have been demonstrated. And because they are sized, so they can also conform to wrinkles, as you see here, because they are, nano or micron scale. But then in this process, you need a carrier such as elastomeric PDMS. You need as a transfer carrier. As an alternate to this, we are exploring contact printing method. And this also opens interesting directions in electronics that it enables roll-to-roll printing, and I'll come to that in a few slides later. So what it does is you have a donor substrate. You grow nanowires on the donor substrate. In this case, these are horizontal nanowires, but here you have vertical nanowires, and this is the receiver substrate. You define on the receiver substrate sticky and non-sticky areas. So, and then you bring them together at a particular force. If you apply particular force and then you slide it, what you get is wires which are aligned in direction of sliding. As you can see here, these are results from some of our wires that we have transferred. And in the process, you get ultra thin electronic layer. Now that's important. If you look at the wafer, it is the top 100 nanometer or so that is effectively used for electronics. And that slice, 100 nanometer, 150 nanometer slice, if you can print, it leads to a new direction within the field of electronics, that you can develop high performance electronics, and that too by printing. So we have some examples here where zinc oxide nanowire based transistor devices were printed onto flexible substrate, as you see here, and we showed that for wearable application that was related to detection of UV. So the technology with this process, then you can go to large area. As you can see, the transfer printing technique shown here, you can pick up wires and transfer them to large area. This would not be possible with conventional technology, because conventional technology is limited to realizing everything on the wafer itself. So with this, you have that flexibility. And we use this transfer printing technique to, one example is shown here, to obtain devices. These are the nano wires, the nano ribbons that you see here, source and drain, and they were then implemented. Array was obtained. We obtained devices which were about 650 mobility, which is quite good mobility when you look at the single crystal silicon based devices. In this case also they are single crystal, because nano ribbon is taken from soy wafer. Those devices, they have about 700 to 800 mobility, and that leads to quite good performance, the conventional electronics. So this approach leads to electronics at par with, in terms of performance, at par with conventional electronics, and with additional features that it is flexible. I mentioned about roll-to-roll printing. This slide shows the vision for roll-to-roll printing, how you could take this research forward and develop the whole system, a pilot line which can lead to devices such as one example shown here, 1T1M, one transistor and memoristor. So what happens is essentially you define your sticky, non-sticky regions here, and you take your separately, you got your if you can get these wires on the roll, or even if they are on planar substrate. So that's the receiver substrate. From receiver substrate you transfer these wires to the so from the donor substrate you transfer them to the receiver substrate, and this color that you see, brown color here, is essentially the electronic layer. If you have to have a controlled density of nanowires, you may repeat this process. So this could be one more step could be added here. And after that, what you need to do is you got oriented nanowires. You can deposit high K dielectric. So ALD, etc., they are compatible with the roll-to-roll process. So you could use these tools to deposit high K dielectric, and then after that you can another step of dielectric here, just to get in this case to show the example of memristor. That way you can realize, and then metal can be printed. Now metal printing these days we have, for example, in my lab a super inkjet printer which can print 1 micrometer line. So those resolutions are nowadays available, and with that you can have high mobility material, shorter channel length, and you could still achieve, by printing you can still achieve high performance devices. So this is an important direction for us. This is important in context with electronic skin, because you have to have the computing, distributed computing as well, and printing over large area also enables the distributed computing. So here are some examples. One of the first version of our printing setup is shown here. One challenge with the flexible electronics is, or large area electronics, is that the equipment is normally not available. So whatever we have, we are either trying to repurpose the existing technology to develop flexible electronics, or you need to develop custom devices, custom equipment. In this case, we developed this contact printing setup that you see here. There's a load cell. This is the scheme shown here. This is the spring, and the donor substrate is attached to the spring. This is to avoid any jerky movements. And then there's a load cell which measures the pressure between donor and receiver substrate. That's the receiver substrate, with patterns showing the sticky and non-sticky areas. And you bring them together, and at a certain force, which is the certain pressure between them, which is the optimum pressure, you slide it and you transfer the wires. The wires we tested for zinc oxide nanowires and silicon nanowires, and these are examples shown here. It's quite good. Orientation is very important, because that that affects the performance. So if wires are aligned in one direction, the performance is much better. And if they are randomly aligned, then performance of transistor goes down. So this work was published in Microsystem Nanoengineering, and this paper also got the outstanding paper award for that journal. How could we extend it towards the large area skin is shown in this slide. So what happens is, this is the transistor made of nanowires. So you got printed nanowires, and that's the array of printed nanowires. So these are printed nanowires you see here, and this is the source, this is drain, and between drain and this could be the ground. So between them you can also include a pressure sensitive rubber. So instead of 1T 1M kind of structure, this is 1T 1 sensor structure, where you have the pressure sensitive rubber as the resistive sensor. So you press this one, and when you press, resistance would change, as you can see from this equivalent circuit. So this resistance would change. This leads to change in the channel current, and that way you can have a printed transistor converted into a touch sensor. Now, likewise, you can also have a piezoelectric layer on top, and you can press it, so that would modulate the channel current again. So in a sense, we are modulating the channel current by integrating the transducer layer on top of the electronic layer. And that's the vision that we have for printable tactile skin. Some examples, some results are already published, and I'll pick up some of these in subsequent slides. And then electronics, because we are printing transistors, some of these electronics can also then be connected to neural-like computing, which again I'll explain in subsequent slides. So that way we have a distributed sensors over large area, and in the back plane you have electronics, which is also a computational layer and leads to distributed computing. So coming to the next part, which is integrated sensing, actuation, and computing. Here is one example that we have developed using this technology. This is a neural transistor, and this leads to a neural-like computing, and that's why I use the term intrinsic computing. So skin that has intrinsic computing. So it works in a way. You can see this is the normal. You may have come across these figures earlier also. You have a synaptic junction, there's a presynaptic neuron, input come to synaptic junction, there's a summation takes place. If it is greater than certain threshold, then you pass on signal to the next level, and there is an adaptation also taking place in the process. So using that as a cue, we developed this device which we call as neural nanowire transistor. So essentially you have nanowire here with the and there's a floating gate realized on nanowire, and then there is a multiple gate. Now these gates have different widths, and this width is responsible. We have different widths because we wanted to define the different capacitance value here. So these are, you see the symbol here, 4 gates are shown, 4 gates are here, and there's a floating gate also shown in the symbol. So this could be treated like this one. So you got 4 inputs. Inputs are going to the gates. So depending on number of inputs excited, you will have the summation taking place here, and you will have if there's an activation function also added to it, you will have the output based on the summation. So that's why you have multiple inputs coming here, summation taking place, and then there's an activation function. You take it to the next level. In this process, you will have transistors working only when the input is above a certain threshold. Otherwise, you will not have input, and that way you can you can scale down the number of scale down the data, and you can handle data more effectively. And that also leads to one of the problem I highlighted earlier in terms of data handling when you deal with electronic skin. So these are the results from these sensor. So when gate 1 is on, you get this response. When gate 2 is on, 3 is on, so it increases, the current would increase. And this is simply, you can get an equivalent circuit. You can make one single equivalent capacitor, and you can see these happening. So what happened then? How does it work when it comes to neural transistor? So essentially what happens is, if you look at the floating gate, the voltage at the floating gate is summation of capacitance multiplied by input voltage. So input voltage is the voltage at these points, at these terminals. So this is the floating gate voltage that we are calculating. And if you do some simple calculations, you will see that this floating gate voltage is summation of CWI and VWI divided by the floating gate capacitance plus summation of individual gate capacitances. And that way, equivalent thing is that you got this weight. So the output, the floating gate voltage is weighted summation sum of the input voltage which are coming to all these multiple gates. And this weight then defines your output. So that's where WEI is equal to CWI divided by floating gate capacitance plus summation. So this way you can develop neural like circuits. So summation that is taking place here. So that's the way you get output. And then we implemented this using the modeling. In this case, a neural nanowire FET model was developed. So that's the neural nanowire FET. So summation, these are equal weighted capacitances. Sorry for that. So these are equal weighted capacitances. You got the inputs, various inputs are going here, and the summation is taking place. And then you got 2 transistors which are connected here, and you got the action output is shown here. So this is essentially a equivalent of activation function, and that the synapse with equal weight, and this is synapse with non-equal weight. And once you get these inputs, so for example, you have 2 synapses, the green, so transistor will work at 4.5, but if 3 synapses are there, it works at 3 volts, and then you increase it works much earlier. That way, depending on number of inputs coming in, you define your threshold, and you define at what stage transistor starts to work. And the one of the bottleneck for this approach is that it does not do real time or online learning, because these capacitance values are fixed. They do not change. And in that regard, we have also done some work. I'll come to the next slide where this is explained. But before that, I would like to show this implementation using the neural nanowire FAT model that I presented earlier. What we did, we developed the 6x6 capacitive sensor array, and the output from this sensor array was fed into the multiple gates of the model that we got, multiple gates of the neural nanowire transistor. And we implemented all these through software, and we could identify that it can detect the point of contact, it can detect amount of force, and it can also detect the direction of the contact or direction of sliding. Now these are important because as I mentioned, you need to scale down the data. So if you look at some neuroscience studies, they indicate that at the point of contact itself, ensemble of the first spike of the ensemble of neurons, if you process that, you can get information such as point of contact, amount of force, or the pressure, and the direction. So one contact, you already at the contact itself, you are splitting that information. You don't have to send this all information to brain and then process to find out how much was the force and how much was what was the direction. This can be done at the point of contact, and that's something we have shown also in this case through simulation, but now also showing it through hardware. And the hardware implementation of online learning or synaptic circuit, one example is shown here. There can be many other examples. You can include memoristive devices, you can use potentiometric arrangement also. But one example shown here is based on zinc oxide nanowire based transistors. So this process is again nothing but the contact printing process that I explained earlier. So you grow nanowires, then you have a receiver substrate where you have polyimide, golden polyimide, so that acts as a back gate in this case, and you transfer them, you transfer in this way. Once wires are transferred, you can realize source and drain, so that makes your transistor. What we noted in this case is when you expose this transistor to UV, the threshold voltage changes significantly, and that is interesting because this change in the threshold voltage can be used as a synaptic circuit, or can be used to change the weights of the neural nanowire transistor that I presented earlier. You can have online training, and this is shown here. For example, this green box that you see would be the place where you put this kind of transistor, which changes with threshold voltage changes with UV. And this is the symbol of neural nanowire FET with multiple gates. As you can see here, these are source and drain. So this is multiple gate connected to each circuit. So input is where you get input coming from touch sensors. In fact, this is an interesting arrangement because it can be applied to other type of sensors also, not just the touch sensor. Wherever you have multiple, it can be input coming from large number of gas sensors, or it can be a combination of physical sensor and chemical sensor or a biosensor. This arrangement would still be will be useful there. In this here you can see example where we tested the device performance under bending conditions. So red color curve is before bending, and yellow color is after bending. Interestingly, we noted that the device performance as a synaptic circuit does not, bending does not affect much. So that is also quite interesting when I look at look from the point of view of electronic skin, because you expect a high degree of bendability there. And how do we go from here? This slide shows the scheme. So you have on the top the transducer layer. Some array is shown here. Top layer is ground layer to filter the noise. Then you got the touch sensitive layer. After that, you have the electronic layer, which I presented earlier. And this electronic layer can also be converted into either it could be readout, conventional readout, or it could be a computational layer. And these synaptic circuits and neural nanowire circuit implementation is shown here. I have shown you some example earlier. In this case, one transistor and one memristor kind of arrangement is used instead of zinc oxide nanowire, light activation based zinc oxide nanowire transistor. You can also use memristor based approach for online learning. Coming to the next part, which is the intrinsic sensing and connected to soft robotics. Currently, soft robotics is all about, some sensors are placed, are embedded, but those are sensors are not distributed. So that's where the current state lies. And in context with electronic skin also, if you look at these worm-like structures, they also feel, they also execute these. For example, these contact points. There's a lot of touch sensing, and I earlier I mentioned snake-like structures. So you have to have skin all over the body. But then skin all over the body means the sensor must be distributed also. And in that context, we have recently developed. I will not go into detail of this device. This is still not published. But we have been successfully distributed sensing material throughout the structure, and we are able to use the feedback from this structure. So there is no single sensor, I must say here. It just the structure itself is a sensor, you can consider that way, and it is all distributed, and we can use this feedback to control the movements as you see here. All I can say is the sensing material is a magnetic material in this case. So that's what we do in terms of intrinsic sensing. Uh, and also we are able to develop the integrate sensing and electronics using new techniques that we have developed, multi-material 3D printing. So normally 3D printing you come across is it prints plastic only, but we design the hand in such a way that you can print the sensors inside the structure. So structure itself could become sensor. You can consider that. So as an example, we start printing the PLA here, and then we print metal lines. We have developed our own. We have modified our 3D printers to print plastic and metal together, and then we leave it this space as you can see this space we leave as either it can be the air or it can be filled with some soft material such as PDMS, and then metal layer again, and then you print PLA again. So that way you have this black structure, which is essentially the bendability you achieve with that. But in the top structure you have the capacitance, and you can then print the conductive layers to connect all vertically. You can connect all the capacitance to digital converter chip is all embedded, and you can connect, and digital signal comes out of the structure. So these are implementations shown here for the entire 3D printed structure. And this videos on the side, they show the response of this hand. These are the capacitive arrangements. So you press them, you can see the response. All phalanges in this case, they have that kind of capacitive arrangements. And this example was when robot hand grasped objects using these feedback based on these capacitive sensors. We have also implemented as a stack of capacitance and capacitance and piezoelectric sensors with fingerprint-like structures. So again, in this case, in previous example was only capacitive sensor, but in this case we have also piezoelectric sensor. And advantage of this approach is that you can detect static as well as quasi-static and dynamic events. So for example, this would be that's when you see the change, that's where your piezoelectric sensor would respond. And when you start again change, piezoelectric sensor would respond. At other points, this is the black color is the capacitive sensor. So you can manipulate or you can you can manipulate or object, or you can feel the texture of the surface with that. So this also includes some neural processing for the data. So that's all I have in terms of distributed sensors and distributed computing. So in a sense, printed electronics was pretty much embedded in the technology that I presented today. And this brings me to the last section, which is conclusion. So to conclude, I would like to say that tactile sensing or electronic skin is important for safe human-robot interaction. It could also be applied to inanimate world in general. So all the objects that you see around, you can think of electronic skin around them. And for electronics, which is the technology or vehicle that is used to develop the electronic skin, is a disruptive area which will add new dimension to the electronics industry, having enormous impact in consumer electronics. As an example, you may think of mobile phone as your wristband. Also in aviation, space electronics, robotics, life sciences, lighting, military applications, telecommunication, and sustainability, which is an important area. I did not discuss much about sustainability today, but printed electronics itself, if you can see the dry printed electronics that I presented, and the waste, that lower waste that we have, intrinsically it takes us towards sustainability. Electronics manufacturing by printing is a promising cost-effective approach. And in terms of high performance, we have used nanowires based on silicon and inorganic semiconductor in general. I did not present any example of graphene-based devices today, but that's we have done also because high mobility was mentioned. So we have done some graphene-based work also, particularly in context with energy autonomous skin. Perhaps some other time I can explain those things. So I would say that together with the organic semiconductor-based electronics, this could be an interesting new direction. Printing high performance materials and organic semiconductor-based sensors, etc., can lead to a heterogeneous integration, which is an interesting way forward. Electronic skin technology as such could underpin advances in several application areas such as bionics, healthcare, Internet of Things, wearable system, and smart cities. Some examples I presented today. There can be many more examples that are available in literature. Here are some background work. If someone is interested, you can go through these works, and some more background work are mentioned here. With this, I would like to acknowledge the support that I'm receiving from funders such as EPSRC, which is Engineering and Physical Sciences Research Council, European Union, Scottish Funding Council, Royal Society and Royal Academy of Engineering, and of course my group members. And that's all from now, from my side now. Thank you very much.
Thank you, Professor Dahiya. That was a wonderful talk. We have actually received some questions. They're posted on the chat window. Are you able to view the chat window, or would you like me to call it out?
Well, I can see the chat window. There are several questions. Okay, there is one question from... Yeah, if you want, you can go ahead or let me know how you want to proceed, please.
Well, Professor, if you can see it, I think maybe you can take the questions as you see fit.
All right. So one question is from Ramachandra K. Practical robotic movement will mean continuous change in the curvature. How are the varying responses handled? So basically what happens is it's a conformal in electronic skin. You integrate skin on the robotic hand on the curvy substrates, and after that the object curvature will not matter much, but because you have your own skin, you can feel those things. So that's how I would say. I don't really get how are the varying responses handled. So is it variation in terms of the surface, or variation in terms of on the weight? For example, I mentioned about lifting a heavy sandbag, which have dynamic area is dynamically the area is changing, but then just because it's a large area skin, you are able to see the dynamic change in the contact point on the skin, and you can use that information to control or handle the object. Then how is the time tagging and sequencing of signals from hundreds of sensors to processing units and feedback to actuation? So at this point, we initially we started with the conventional, row column fashion, and then if you look at the triangular patches that we used, 16 triangles, there was on top of them there was a microcontroller. So at the the patch made of 16 triangles, we handled that data, passed to microcontroller. Then from there on, I2C communication channel was used to again transfer data to CPU. So in this process, the lot of data was left because processing was taking place at the 16 triangle set level. So basically, significant amount of data was not transferred. If you look at the hand, so if it is not in contact, only contact points which were detected signal were coming, the data was picked up from these points only, rest was neglected. So if there is no contact, then there's no point in, let's say if I'll take this hand, if you look at this pen, only contact points are the fingers, and there's no need for to read the data from rest of the points. So we were looking at the change in the response of sensors. So wherever you saw the change in the response, you use that data. So that was the way sensor data was processed. Uh, then there is a question, any thoughts on the robustness and self-healing? Self-healing is a quite interesting dimension. Certainly, something we want to achieve, but it's a problem mainly related to materials. We have not been able to achieve quite good results there. But there are ways, for example, liquid metal are being explored these days for this kind of application. Self-healing is also relevant to electronics. For example, interconnects. So when you bend the device, interconnect may break, and in those cases, you may think about interconnects which are self-healable. And robustness, we test our devices over a large number of bending cycles to see how performance degrades or performance improves. So bending is not necessarily leading to poor performance. Normally, we believe that bending would lead to poor performance, but I can give an example that straining devices can also lead to higher mobility, and that way you can improve performance. So robustness is addressed by testing the device over large number of bending cycles. And some example I gave you when I was talking about synaptic circuit, where we bent over the device about 100 cycles, and we noted there was no appreciable change there. Then there is a question, what is the typical power requirement for flexible device? Have you used piezoelectric energy harvesting technique to power the device? Uh, as far as the power requirement are concerned, currently we have not really looked at that aspect when I see the electronics, but the goal remains that it should be low power. Sensor part we have been more careful about in terms of power. We have used graphene-based capacitive sensors, for example, which require as low as 20 nanowatt per centimeter square. And electronics is normally more or less electronics. The power requirement is same as conventional electronics. So we have not done, from electronics point of view, we have not looked into the power. But we have been looking at power energy harvesting. To address this issue, we have used solar cell-based approaches. We have used piezoelectric approaches. We have used triboelectric energy harvesting. As I mentioned earlier, energy part I did not cover in the lecture today. So we have developed triboelectric energy harvested for wearable systems, and we are using them for large-scale implementation, which includes harvesting from waves also. There's a question, okay, sensors can be used in many different fields. I have a question regarding suitability of material in harsh environment. Devices were sandwiched between polyimide, how device can behave at high temperature and durability. It's a good question because harsh environment, there are several applications where electronic skin can be used and harsh environment would be needed. My answer here would be polyimide is not the suitable material, particularly if a harsh environment has high temperature. Polyimide among various flexible materials is the best because it can withstand up to 400 degrees. Others would melt at 150 to 200. So that way polyimide is slightly better. But you can also use metal foils also if you go to high temperatures, and you can still then use the printed electronics. So metal foils, then you deposit some dielectric on that, and then you can use that as substrate. It would still be flexible. You have to think about how the temperature itself would change the performance of electronics. Perhaps by using other materials, not silicon or zinc oxide, but using materials that are currently used for to develop electronics for harsh environments, we could explore that. We have not looked into this aspect at this point. So, do you see system performance degradation? I think I've already answered this question. degradation could be there, but you know, if we use the knowledge that we are using for 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 harsh environments at this point, perhaps we could also use compensation circuits, etc., to make sure that performance remains stable. Uh, then, which would be the most suitable material for haptic sensing? Well, there is no clear answer, I would say. It depends on how sensitive feedback, how sensitive the sensitivity requirements for the application. So it could be a soft material. Uh, the range of materials are can be used for haptic sensing. Now, I must say that haptic is a word that should be used for two-way transfer of information. Normally, it is confused with the touch sensing, but touch sensing is part of the haptic sensing, allows you to transfer information from object towards brain, but then there is a signal also coming from brain towards object, and that's where actuation would come. So you have to take complete cycle. And we have done some work here. I did not cover it today. We call it Sensec device. I did not cover because it is subject to IP. It integrates sensors and actuators together, so you can see that you can have that real feedback, and soft materials are used there. So soft materials such as Ecoflex or PDMS are used there. If you want haptic sensing like skin, then you definitely have to look for soft materials. So then there is a question from Darkasha Khan. So how is the applied force being detected? And what is the time delay as there is so many sensors integrated together? So applied force is, as I mentioned, it depends on the sensor. You can have a capacitive sensor as an example. When you press the capacitive sensor, distance between two electrodes would change because the dielectric between them is a soft material, and that leads to the change in the capacitance, and you detect change in the capacitance, convert that value into digital value, and then you can further process. Likewise, in case of piezoelectric materials based sensor, when you press them, they will lead to additional charge generation. And I mentioned, if let's say piezoelectric sensor is present on transistor, that could lead to modulation of channel current, and then you can use it further electronics. You can integrate. So the delay depends on time delay, depends on the material again. If it is soft material and quite thick soft material, then it will take time to regain. So there are various dimensions to that. Normally, piezoelectric sensors are very fast. The range, it's milliseconds, less than milliseconds response we have noted. So in those cases, we have not seen significant delays, but there are capacitive sensors where we have seen the response coming in order of seconds also. For real application, you need to have very fast response. Would you suggest, Sujata asked questions, would you suggest a piezoresistive material to use on polyimide film? Well, there are several materials that could be used. I mean, even you could use zinc oxide nanowires as a piezoresistive material, or you could use the bendability itself. You know, you on uh, well, okay, I'll continue. It looks like piezoresistive materials. So as I mentioned, there are several materials that are being used um, for piezoresistive layer. And one example I mentioned, zinc oxide nanowires itself, which we print, could be a possibility. Other examples you can pick up from silicon nanowire itself could be, when you bend the resistive property changes, and then they also could be used as sensors to form polyimide film to achieve the various sensing properties. What are the applications in aerospace areas? Well, electronics can in aerospace area, you can think of uh, uh, let's say robotic going to space station, and instead of humans you want to send them to space station to, and a tool handling etc is very important. So for those tasks, electronics would be quite important if you connect through robotics. but also in other areas. So in this case, in context with robotics, it's all about pressure and temperature sensing. But you can think of, as I was mentioning, zinc oxide nanowire based wearable dosimetry device that I mentioned, which can detect UV radiation. So you could think of electronic skin with different type of sensors, which measure the sensors measuring. The inputs from various other kind of optical stimuli instead of physical or chemical stimuli. So I would connect more in context with robotics though. So harsh environment question I have already answered. Then there is a question from Ashok Kumar. There is a focus on 3D printing application on printed sensors. How far we reached in realizing reliable printed sensors? Well, I have given an example where capacitive sensor was printed. And currently we are working with a leading robotics company to realize their hand with those embedded sensors. So that's, I would say, I would call it a low hanging fruit. In a sense, it can be realized very soon in immediate near term. What is the typical density of sensors? That depends on application. The density of sensors, the tactile acuity in the fingertip is about 1 millimeter, which means that if you press 2 points closer than 1 millimeter on your fingertip, you will sense them as 1 point. So, and more than that, so that defines basically the density of the sensor. So 1 millimeter apart. But if you look at the back, then it can be 3 to 4 millimeter apart, up to 1 centimeter apart. Then you don't need that level of sensitivity. So it depends on the parts. If the task is being carried out through hands, then you need highly dense sensors. And if the whole body is required, then density can be there is a flexibility there. Then V. Sudhakar asked, can we use them for passive sensing like pressure monitoring or on aerofoil? Well, definitely yes. If you consider an example of wings of aeroplane, if you can want to measure the stress, then there can be such sensors could be electronics in concept could be used in those applications. How much electronic support system on board required? Is it similar? So fiber bright gating is a different technology. It's optical light based technology. I mean, here we are talking about distributed electronics, and in that case, that's more about the sensing the fiber. So you touch at some point, and then you measure the change in the light conditions. It would be difficult to get with fiber bright grating. It would be difficult to get the kind of electronic skin that I mentioned because the contact point itself becomes quite difficult, quite challenging there. So then there are some, okay. Well, I think there are no more questions. These are all they are appreciating, and thanks for that. Thanks for appreciating the presentation. Yeah, that's all. I hope I have answered most of the questions.
Yes, thank you very much, Professor Dahiya. Now I'd like to call Dr. Veda.
Thank you, Professor Dahiya. It was a wonderful talk, and I would actually like to thank Dr. Rudra Pratap also, because I remember after we thought of inviting you, I just had to mail him one night, and the next day morning, I knew on my inbox there was a mail written to you. He was that prompt and that quick in getting me connected to you. So a special thanks to Professor Rudra Pratap. And special thanks to Professor Dahiya. I have heard your talk earlier in the IEEE Sensors Conference. So that's why I thought that we can have you on IEEE platform. Now I request Professor Rudra Pratap to just come online and say a few words about Professor Selvarajan, in whose memory we are having it, and conclude it. So please.
Thank you, Veda. Am I audible?
Yes, sir.
Yes. Okay. So first of all, Ravinder, thank you so much for a wonderful talk covering so much on this technology. That was really nice. Of course, I must tell you that we were delighted once you accepted for this talk, because this is a very special talk we have that we do annually in memory of Professor Selvarajan, who started these microsystems work at IISc. He was the first person to work in this area. Professor Selvarajan, a very, very soft-spoken man. Okay, he was in ECE department. He was chair of the ECE department. He served ECE for probably 40 years. I don't remember exactly, but he was there for a very long time. A thorough gentleman whose very presence in a meeting will make us all feel so comfortable, to talk about anything. And he was the first person who started this whole idea of putting together a society, be smart, or working with Professor Atre, and the rest is history, as they say. Whatever we see is the culmination of that effort. I got to see Professor Selvarajan only after he had retired. That's when I joined here. And, after his retirement, for almost, 15 years that I saw him active in this area, he was always encouraging all of us to take up this area with more vigor, work harder, do technologies, always very, very sort of gentle. And I have very fond memories of him, and so do my colleagues in ECE as well as in IISc in general. And this entire ISSS community of members fondly remember him. So it's really nice of you to give this memorial Selvarajan Memorial Lecture when we also think of him and we remember him. Thank you once again.
Oh, well, thank you very much, RP. Would have been great if I was there to give this lecture instead of doing it online.
Yes, there will be those chances for sure, Ravinder, because
Yes.
I don't know.
We'll wait for an occasion to bring you here.
Well, thanks a lot.
Professor Atre, you may or may not know, but
Only the outstanding lecture. I have heard about this flexible electronics so much, and I think you made the day. And
Ravinder is also
as
Satish Dhawan Chair
group of
Professor.
in memory of Selvarajan, it was an outstanding lecture.
Yes.
Maybe sometime when the COVID is no longer there, we will bring you to Indian Institute of Science and perhaps have a much more detailed talk from you on an outstanding technology. Thank you.
Well,
Thank you.
yeah, definitely that would be a pleasure. As RP was mentioning, I have more connections now with IISc. Definitely, that would be a pleasure. Yeah.
He's Satish Dhawan Chaired Professor at IISc. So he's a visiting professor for next few years, and he will be visiting us. Actually, he was supposed to, but
Yes.
COVID had different plans. So
Yeah.
we
will assure you warmer weather.
Yes. Okay, Veda, back to you.
Thank you.
Thank you. Thank you, sir. It's been a great evening starting from the HM, and we are concluding with such a wonderful talk on a very, very high-tech technology. And we hope in the years to come, in the days to come, we can have collaboration with Professor Dahiya on the ISSS platform. We look forward to its talk. Thank you once again, everyone. And we conclude the session here. Thank you.
Thank you very much.
Thank you.